Thank you, Sam. Thank you, Andrew, for the invitation for this presentation. Those who are a bit older among you, they know that I have been around in this analog and mixed signal space for a very long time. I actually did my own PhD in this area, but we are talking now about the period 86 to 90. And the thing is that since then, the problem has not been resolved at full. So we are still struggling with these analog mixed signal designs. And actually the problems have become worse than before. And that's why I now try to explain to you, give you an overview of the next wave of attempts to address this issue. And that's why I call it Analog Synthesis 3.0. I will not only focus about sizing or synthesis of the analog circuits, I will also talk about testing of the analog circuits, because we are also using, because that's also a big issue, and secondly, we're also using machine learning techniques there to help improve the testing problem. And as Susan said, I'm at the university in Leuven. Here is the outline of the presentation. I will briefly mention the challenges that we have in analog mixed signal IC design, give a glimpse about the early approaches, so analog synthesis 1.0 and 2.0, and then I will talk about, give an overview of methods that have been presented in the analog synthesis 3.0, and then focus on the machine learning in testing and wrap up with some conclusions. Analog mixed signal circuits, as you may know, we are in a digital world. Everything is digitized, most applications are digitized, which means that our electronics run with digital circuits, but the signals in the real world are analog, so we need analog mixed signal circuits at the interface between our digital circuits and the physical world. This is a graph that I copied from Paul Gray when I was doing my postdoc at UC Berkeley back in 1991. And already then he said, well, this analog shell will never disappear. And actually, the bigger we make the digital core, the bigger the analog shell will be. And that's exactly the case. And so you see that this analog is needed in almost any application. Even though it's digital, we need the interface circuits. And I'm pointing out to a few recent ones like agriculture and environmental applications, where we also use a lot of analog and mixed signal circuits. Consequently, you also see the market growing. So these numbers are the total semiconductor market the total semiconductor market has a growth similar to this with 618 billion today. These numbers are the market of analog and mixed signal circuits, and you see that driven by a number of applications such as everything related to environmental sensing, everything related to IoT, Internet of Things, makes the analog mixed signal market booming in recent years, and it's now at about $84 billion in 2022. I am from the KU Leuven. At KU Leuven we have a research group that is focusing entirely on electronics, on design of electronic circuits, and we have there 6 professors in different areas focused on electronics only. Together we have 80 PhDs. Some of my colleagues deal with millimeter wave circuits, RF circuits, digital circuits, AI, accelerators, etc. My focus there is on analog and mixed signal circuits and on design automation and testing for analog and mixed signal circuits. We cover the whole space from DC or sensing applications up to terahertz frequencies, and we do that in whatever technology we can have commercially available to us. We do not develop our own technologies. That's work for IMEC, the research institute next to our university, but we design in commercially available technologies, and I must say that the most recent ones are also quite expensive to do research in. We do have, so fabrication of chips is done outside, but we do have everything else in terms of infrastructure that is needed in order to dice, to bond, to package, to measure and characterize the integrated circuits that our PhD researchers have done. And here you see a few snapshots of that. Before going on to the machine learning, two examples of recent designs that we did. A very important research field in Europe is automotive. And so we have been working on sensor readout circuits. The number of sensors in cars is booming. And so they all need readout circuits, and they always need to be cheaper and cheaper and cheaper every year. Why? Because they want to put more sensors in a car, and the car must be at the same price level almost. So that means that the price per sensor has to go down every year. And so we developed a new way to develop these readout circuits that results in a very low area, and area is directly reflecting into the cost. And the new way is the fact that we do it not in a voltage domain readout, but in a time domain readout of the chip. And still we managed to show that after some research we achieve the same performance as in the voltage domain, so 16-bit of resolution. Another application is in the biomedical space, where we are developing electronic skin applications. For instance, for robots that you want to give the same touch and feel as humans, or people with prosthetic hands who get the same touch capabilities as real hands. There are these things today, but they don't have the resolution as our human hands and human fingers have today. And so we developed a chip for that with an array of 12 by 16 taxels that can be read out and then locally processed with some complex receptive fields to reduce the information that is then sent normally to the nerve system in your body. In this case, it's connected electronically to the robotic thing. This chip was presented recently at the VLSI conference. And then finally, last example, we also work on neuromorphic designs to do information processing in the edge. So we try to make applications that have a good performance for the application at hand, but at the lowest possible power or the lowest possible energy, lowest possible latency. So that means a lot of processing locally in the edge device itself. And so we are working on spiking neural net systems, for instance, but we try to build in self-learning capabilities into the edge device that can learn to reach a good performance without pre-training, because we don't have enough labeled data available to train things big for these edge applications. So we are working on algorithmic ways to do this self-learning, and then we work on implementing that efficiently in hardware. Now back to the machine learning. So these analog circuits, of which I showed you a couple of examples, if you look at the design in industry, yes, they're using a few tools here and there, but they are not synthesized automatically in the same way as digital circuits are being synthesized. So there's a large manual effort involved, and as you can imagine, that results in long design cycles, and that also results in lots of design errors. And so this is a report from Graphics where they reported that even though the analog part of a mixed signal SoC is not the biggest part on the chip, it contributes to the biggest chunk of the design risk, causes the most problems in the design of these blocks. And if you ask me why is this the case, well, it's a very highly complex thing to design an analog circuit. The search space that you have is highly dimensional. There is not a very clear sense of abstraction levels in the analog domain. The hierarchy that you would consider is also not so clearly defined. And above all, the analog circuits are sensitive to almost anything that can vary, temperature, process variations. So all this makes it a very difficult task that results in long design times, high NRE costs, etc. And so the question here is that we should find better and more tools that can address this issue so that we can increase the productivity, reduce the design time, and above all, reduce the risk in designing these analog mixing circuits. Now, how does the design of a circuit goes about? If we take a typical flow for a low-level circuit, a basic circuit, let's say an amplifier, you typically start with a list of specifications that can be more than 2, of course, quite large. The designer chooses a schematic or a topology that, according to his or her knowledge, can meet those requirements, and then you size that circuit, meaning that you determine the width and the length and the biasing current and the biasing voltages of every transistor and every component that you use in that circuit, such that the design circuit meets the requirements. Then you go to synthesizing the layout of that block. After layout, you can do an extraction, including all the parasitics, and you do a final verification check. So that's about the typical flow. If we look at these steps, topology selection today is done mostly manually, based on the experience of designers. Now, does a designer choose the best topology? That depends on his prior knowledge. Sometimes they know a lot of schematics, sometimes they only know a few, and they stick to those few. So there may not be a fully optimum choice there. But the main issue is here in the sizing, because here we are confronted with the curse of dimensionality. There are many design parameters. Even for a simple circuit like here, you have many parameters to be decided based on the initial requirements. There's not a one-to-one unique solution, so there's multiple solutions possible. The different requirements conflict with one another. Process variations and temperature variations have an impact that has to be considered and all that. So managing all this high-dimensional problem is quite an issue. And the way how human designers do that is they, over the years, sometimes maybe by trial and error, they develop some heuristics, some heuristic approach how they can get to a solution in this space. And that's why it's difficult for a tool to do that, because how can a tool find that same solution if the tool does not know those heuristics? The layout phase is also complicated in recent years because the number of design rules that has to be considered is growing. So if we go to more and more advanced nodes, you see that the number of design rules that have to be taken into account in the layout synthesis is also growing. That was a basic block. Of course, when we are talking about a real circuit, like a front end or a to D converter, obviously we have to do this process hierarchically in different steps, where you first divide the front end into sub-blocks, which are then again divided into sub-blocks, and eventually you have these low-level blocks in the middle. How did people try to automate this process in the past? Well, it's clear that you will not easily find one tool that can do everything, because if you look at the mixing LLC, you will need different blocks. And so some of these blocks, like certain converters, maybe you develop dedicated generators for these blocks. Why? Because they are used so often in many applications that it makes sense to have a generator for that block. Same for passives. If you use a capacitor or a coil, an inductor, you may have a generator for that. But for other blocks, their reuse is so low that you would probably want a custom synthesis tool where you give it a schematic and you give it your requirements, and then it cranks out the optimized circuit. One of these examples, generators, is work from David's group here. It's a SAR, successive approximation register A to D converter, and it can generate these SAR converters from specs all the way down to layout. And so you give it the requirements that are needed, and then it cranks out the digital parts and it cranks out the analog parts with optimization of the circuits and with generation of the layout, and then it gets a final layout that is then verified. And they have also presented a few designs that I've generated with this, and you can find also some of their results in design journals, generated automatically with these tools. But as I said, we cannot build generators for every block that they use in these mixing SoCs. Why? Because if you look at an SoC, there are so many blocks, so making a generator for all of these would be too complicated. Every block itself has many performance parameters, and in many applications today we cannot afford to have non-optimal solutions, because that would consume too much power or too much area, and that's why people want an optimized thing. So we need to synthesize it. Now if we look at the history, this interest in automating the process already came about in the early 80s, and those who remember, that was the early days, the first wave, at least that I remember, of AI techniques. Only the AI techniques used in those days were expert systems. So people wanted to try to figure out how an expert did a job, how a doctor, a medical doctor, does a diagnosis, how an analog designer designs an op-amp. And they tried to figure that out by interviewing those people and then coding that into some scripts to do, or a rule-based system, or a script or something like that. And then they had the script running, doing the same thing as the expert had told them. So that was the early approach, knowledge-based. I come back to that in a second. Then later on, as we all know, those expert systems didn't fly. And then there was a second wave of approaches to address the issue of analog circuit and layout sizing, which is the optimization based approaches, because they use the power of optimization algorithms to synthesize. And then finally, in the last decade, last 5-10 years, you see a third wave of approaches, the 3.0 wave based on machine learning. And I make this a bit higher here because I hope that the outcome now is more successful than the previous approaches. So the 1.0 wave of approaches was knowledge-based, trying to encode heuristics knowledge from designers into scripts and execute these. And clearly there were some tools developed that could nicely design circuits, but two main issues is, one, it's a huge effort to do all the interview, make the scripts general, and so they are always inflexible, because if I ask 3 experts how do I design the same amplifier, I will get 3 different answers. So that's very difficult to get into a tool. The second wave of approaches are the optimization based, because here 2 things happened. One is the power of computers was increasing to a level that we could do this in acceptable CPU times. And secondly, there was an enormous progress in terms of optimization algorithms, starting with techniques such as simulated annealing, then going on to genetic algorithms, evolutionary algorithms and so on, multi-objective genetic algorithms. So there was a huge progress in the algorithm side, reflected in a huge progress in this hardware side. And so the way how circuit sizing and layout synthesis were set up is by combining some optimization algorithm with some evaluation engine, such as a SPI simulator, and then have that iterate many times until you get an optimal solution. And also here there were several successful tools developed, and what could we see is that on the good side, these tools sometimes got results that were much better than results generated by human designers. So don't tell me that tools cannot be better, or don't tell me that human designers are always better than tools. That's obviously not true. But the results of the tools are only good if the designer has entered proper constraints. Without proper constraints, sometimes the results of the tool are, in some sense, optimal, but not useful. And that's an issue. So you need to set the right constraints so that the results of that long optimization loop are useful for a designer. Here are some of the snapshots. Sizing can be done better than human designers. Layout can be generated better than human layout technicians, etc., but only with the proper constraints. And one of these constraints is, for instance, the fact that it has to be robust, even if the process parameters have their variability, even if the temperature or the supply voltage change and so on. And somehow designers take that implicitly into account when they design a circuit. Now, implicit does not exist for an optimization tool. It has to be explicit, and that's the challenge. So there were a few attempts to try to extract that knowledge, those constraints, automatically. And I mention here some early work that I did trying to grab lots of these things through symbolic equations, and Helmut Grape and others have also tried to automatically derive constraints out of the schematic. And they made some progress, but they didn't get the full solution yet, so that if you give a schematic, constraints are generated automatically so that the results are correct. That's why I think industry sometimes uses a bit of these tools, but not all the time, and still a lot of manual effort is being done. But in the last 5 to 10 years, we have experienced a new growth of the next generation of algorithms. I would not say it's a discontinuity, it's just a new breed of advanced algorithms based on concepts of machine learning. And obviously analog design automation, analog synthesis is also one of the application fields where these algorithms are used. So that brings me to the third wave. In this case, the machine learning techniques were originally used in this context to speed up the number of simulations that would be needed in order to synthesize the circuit. Because you have this optimizer in the loop with a simulator, so this runs for a very long time. So if somehow you can reduce the number of simulations, you would get to a result faster. Or if you spend the same time, you could handle more complex circuits. So how could we do that? Well, we could somehow replace these simulations with a model. And people developed all kinds of analytic models that could be generated on the fly, Gaussian process models, and eventually machine learning models, neural network models. They could model the performance of a circuit equally well, and instead of doing a full simulation, you can do that through a model. So that was the initial goal, and that reduced the number of simulations. Later on, they said, okay, we can do more with these neural network methods. We can use them to synthesize the circuits themselves. And then you come to this approach where in most cases they were using reinforcement learning, where you train the network in a way that you optimize some kind of reward, which of course corresponds to the performance of your circuit. And so once this has been trained properly, you can easily do a synthesis using that trained model. And different techniques different tools got developed that were using some sort of this approach. And I will mention a few in the next slides. It's not going to be an exhaustive summary, but just a few. But of course, there are a few challenges. And one is that with any neural network, you need good training data. That's always a challenge. Secondly, we are not synthesizing a circuit for only nominal conditions. We have to take robustness, process variability, supply and temperature variability into account. And finally, when you get outcome of any of these machine learning methods, explainability, explaining why that is a good result, especially if it's different from what the designer expects, why that's a good result is also important. And I don't think that many of today's methods can already do that very well. One example here is the auto circuit or back approach developed at UC Berkeley, where they train network using deep reinforcement learning. So starting from some requirements, so they actually sample the space of the requirement. They take a few samples in this space, and then they optimize the design, so that they have a kind of model built of the entire space. And when they then have an actual design towards specific applications, they select some of the nearby points and use that in order to, from there, take the final design. The thing is that because they already have done this work, is that the whole thing is more sample efficient than just a full optimization from scratch. And they also included the back tool in order to create the layout. Here you see some results. So this is the number of simulations, and here is the reward function. So 0 is good. And so the three curves are actually, the green one is without any constraints added, and as you can see, it'll eventually get there, but after many simulations. But if you add typical constraints, such as matching requirements, you see that it gets to the result in a much shorter time. So again, also here, yes, you can do it with reinforcement learning, get to good results, but adding constraints is a key thing to get there fast. Now, process variations is a concern that has to be considered. Now, in this paper presented at this workshop last year, she and his co-authors addressed this issue of PVT variations. They had not one reinforcement loop, they had multiple reinforcement loops corresponding to different situations in that PVT space. Obviously there can be many, so they kind of pruned it a bit to the set of key combinations, and so they can do their whole sizing taking these different corners into account in order to then come to the final solution. And once in a while they have to check that everything works for all corners, and that's then this outer loop that they can do to check that the pruned version still covers everything. So in this way you get a design that is optimized and a design that is robust at the same time. And here you see some, again, the number of simulations, and you see how they were able to show that the number of simulations required with their approach is a lot less than with other competing algorithms. And then the last one I want to present is this MARL approach presented at DAC this year. Remember that if the circuit is more complex, we approach it hierarchically. So if you have a complex analog circuit which you split up in different blocks, you can have a reinforcement learning problem or reinforcement learning algorithm for every subblock. And so that's what they do. Reinforcement learning loop here for this subblock, for this subblock, for that subblock, and then some way to deal with the interactions between the blocks. And that's what I did in this paper. And so in this way they had a global optimization and subblock optimizations all running together. And in this way they were able to design complex circuits of the level of a SAR A to D converter, something like that. For more details I refer to the DAC paper. And then a last example is not on the sizing but on the layout. I want to mention the Align tool from Sechin Sapatnikar's group, where they can turn a sized netlist, so something that came out of the previous slides, into a full layout. And to do that they use primitive generators, so generators for transistors or matched transistors, differential pairs, things like that. And then they use placement tool and floor planning and routing tool to come to the final layout. But they use machine learning models in order to help them during this synthesis process. For instance, when you do a placement, you have to have an assessment of the impact of the later routing that you do. And so they can have a parasitics estimation built on these machine learning methods that can be used during placement to estimate whether a placement is going to be good or not before you've done the actual routing. And so here are some of the example layouts that they have published, different amplifiers, equalizers, and so on. Finally, I must say My ERC project, which has started last year, Analog Create, is of course taking these results, but taking them a few steps further. Constraints are a key thing, and it's very hard to ask the designers what should be taken into account. But when they have done a design, it is in there. So the idea that I want to explore in this project is to self-learn the constraints from existing designs. Try to learn what designers embed in designs through the designs that they have made. So we don't have to ask them, we just extract it from what they produce as output. So in that sense you can say it's no human in the loop, because we don't ask explicitly. And you can say, yeah, but how many SAR converter blocks will you have available? But I think most of the knowledge is at the level of the subblocks, and so that's where there's a lot of subblocks that are going to be reused among different designs. Now, when we extract that from given designs, I also believe that we can, through some form of transfer learning, that we can project this knowledge onto other circuits. And so the key is to discover the basic underlying principles and then apply that to other circuits. And finally, I also want to create novel circuits. Now the designer always gives the schematic. I think that we can maybe create new schematics, maybe schematics where designers haven't thought about yet. And to do that, we represent the structure through graph neural networks, and we use some sort of generative AI techniques in order to find new schematics. But again, we had a discussion yesterday evening that explainability, because if you obtain some result that is non-traditional, designers will not believe it, will not accept it, will not use it, unless you can explain that it does work. Anyway, that's the project, and I hope that some of my students will be here at this workshop next year to present some of the first results. That is about the synthesis part. Now I switch gears on the testing. Testing is a necessary part of our chip fabrication process, because the fabrication process introduces defects, is not perfect, and so that means that some chips will not be working after fabrication. Now you don't want those chips to be shipped to your car. So that's why the industry tries to detect them, and to do that they do testing. They test at wafer level, they test after packaging, before they ship the chip to the customer. But testing does not take forever, testing cannot test everything, so some chips still escape and make it to the customer. Still, I want to reduce this escape rate, and the target in the industry, especially in the automotive industry, is below 10 ppb. Obviously, the target is 0 ppb. The reality is below 10 ppb. And so, what is the current situation? The current situation is that we are somewhere around 100 ppb. So that means that still, if we fabricate 1 billion of chips, 100 of them still have a problem that goes undetectedly to the customer. Now, not all of these problems are critical. I mean, the car will not crash, the car will just stop driving. But we want to get this lower, and the question is, can machine learning techniques help to do this? And so we are talking here not about process variability, because that's addressed at design time. We're talking here about the defects at the moment of fabrication. And most of these returns that you have here, most of these are latent defects. So I first show you a few examples of non-latent defects. So these are really an open circuit in a via. Obviously this creates an open circuit and the circuit doesn't work. Or some metal that is left here and that creates a short between these lines that should not be there. So that circuit is also not working. But these are there at the moment of fabrication. And in order to detect these, we have developed, similar to what the digital people do, we have developed a defect-oriented test methodology where we model every possible defect that can occur in a circuit through some circuit simulation model. Here is, for instance, an example of the 6-volt model for MOS transistor. We insert each of these 6 volts one by one into the circuit netlist. We can then simulate the performance of the circuit for the test stimuli that we apply during testing, and then you get the simulated outputs which you can process, and based on that you can decide, okay, this circuit in testing is working or not working. And of course we have to take the process variability into account, so these simulations may be Monte Carlo simulations. And so in this case you can, through simulations, fault simulations, determine the coverage of the total number of faults that you consider, the coverage by your test program. Because of process variability, if you do your testing, and I show here the probability distribution function of measured values for some performance that we measure during testing, and because of process variability, it will have a distribution like this, centered around the nominal value. Now, if the circuit has a defect, it has another nominal value and a distribution around that. And so the fault coverage is actually how many of is the percentage of the faults that can occur in the circuit that you can detect through your test program. Now this fault coverage will never be 100% because, as you can see here, the distribution of the faulty circuit and the distribution of the fault-free circuit overlap. Therefore, if you test and you set certain boundaries for your testing, for instance, this is the nominal performance, and you say, okay, if it's outside these two boundaries, then it's a bad circuit. Then there are two things that happen. One is that you throw away some of the good circuits. So these dashed ones here, you throw them away. That means that you have some yield loss through your testing. And the second thing is that because of the overlap of the faulty circuits with the fault-free, you allow some of the faulty circuits to enter, to pass the test. And so you have a non-100% fault coverage. And to increase that, to increase the fault coverage, what can you do? You can increase the number of tests or the amount of analysis that you do on the tests, and you can also improve access in and out to your chip by having DFT circuits added. But both come with a price. More tests means more time needed for testing, and DFT structures cost you extra silicon area. We have developed and applied this methodology to industrial automotive circuits, and by adding a few extra DFT configurations that are used only in test mode, we have been able to increase fault coverage up to 98.6%, which was way better than the traditional approach. Still, it is not sufficient. It's not sufficient, and therefore we have been thinking about approaches to further increase the coverage. And the first approach we did is, okay, we test this data, and now we thresholding. but maybe we can do it in a more clever way and get more information out of that by using machine learning method. So we train a machine learning, a neural network, machine learning model. We train that based on data from past measurements or data generated with the fault simulator, and then we feed that to new test data, and then that trained model can do a classification about whether, according to the model, it thinks that the chip is good or the chip is bad. So do a classification based on test data. And using this approach, the machine learning model with proper input stimuli, we have been able to show that we can get fault coverage values that are in the range of 98–99%. Be it the higher the fault coverage, the more yield loss you have. Yeah, so there's always this trade-off. If you detect more faults, you will throw away good samples. So these results were okay, 98–99%, it's good, but it's not 100%, it's not 10 ppb. And in particular, what are the most difficult defects to detect? That are the latent defects. Now, what is a latent defect? A latent defect is something that is not correctly fabricated, but that is not completely a defect yet, right after fabrication. So here you see this pinhole. It's something that is in the gate oxide of a transistor, but it's not a full cut through, because then you would see it cut through the gate oxide. It's partial cut through, but you can understand that if we ship this to the field, that after 1,000 kilometers of driving, it will be a full breakthrough. So it's latent at the moment of testing. You don't see at the moment of testing, but it breaks later on. And for the user of the car, it's the same. Whether it was latent or a real one, the car breaks. So we should test these things before shipping it out. Now you can say, well, these are outliers. Forget it. They are not outliers. As you can see here, this is data from real chips that came back from broken cars. And you see that the value of these chips, we traced back the measurement results of these chips. And you see that the value of the original measurement results are all over the distribution. So they're not really outliers. So the question is, how can we detect, I'm coming to the end as you can see, how can we detect these? And we said, okay, maybe we can use the power of machine learning, because machine learning can find patterns in data. And so we developed a machine learning model that can take the data from a standard test program and do some post-processing according to the machine learning model on it to detect whether there was, yes or no, a latent defect. Now, they passed the original test program, so what can we add additionally? We can add additionally that we combine measurements under two different conditions. Two different temperatures, two different supplies. So the machine learning model combines these measurements under different conditions, and what turns out to be the case is that chips with a latent defect behave differently under the two different conditions than the fault-free cases. And that difference is detected by the machine learning model. We use support vector machines to do that, but here you see the results. Again, the coverage getting up to 98–99%. In this case, coverage of the latent defects, and then versus the yield loss. And we have measurements at wafer probe level, at low temperature, high temperature, and then you can do the ensemble. And the ensemble of the three machine learning models gives you very good results. So the machine learning can get information out that you would not get otherwise. So that brings me to the conclusions. Analog design productivity and risk are a big issue. This is why we need tools. Optimization algorithms are powerful but suffer from constraints, and that's why the machine learning methods are the next wave of algorithms that can help us to get to these good results. The reinforcement learning is powerful to do the optimization. We can extract knowledge and learn that to other circuits, and I'm trying to use generative AI to create new structures. And then in the test space, these machine learning methods can help to improve the coverage also for the latent defects, bringing the coverage to the 10 ppb range where it has to be. Thank you.
Many thanks. Yeah, many thanks for the very informative talk. So lots of techniques, and we are running out of time, but definitely we have time for questions. Please.
Will you be referring to the slides, or can the students switch the laptop back? Is it okay to switch the laptop?
Yeah, it's okay to switch the laptop back.
Questions for the keynote speaker?
Maybe I start with one quick question for the last case study where you talked about those latent defects. Don't you have the problem that those are rare cases where you don't have enough data to validate or to...
Absolutely.
For machine learning where they are very data hungry?
Yeah, this is true. And we were very lucky that we do this project together with an industrial partner that is a semiconductor company in the automotive IC space. And they worked with us to design and fabricate a chip where intentionally we introduce these pinholes.
Okay, that makes sense.
Now, in order to do that, you need an extra fabrication step, and that required an extra mask. So what we did is we used an existing product. We were able to reuse all the existing masks, and we introduced one extra mask step, which is after deposition of the gate oxide, and before the poly is deposited, you do a partial etching of the gate oxide to create those things.
Okay, that's very
and then we had thousands of chips.
You have enough data then?
We have enough data.
Okay, to control it.
Yeah.
Please, Andrew.
So the original title that's in the program was Hope or Hype, and also you showed 3 waves about 2 decades apart.
Yeah.
What would 4.0 look like, or will there be any need for a 4.0? And what's the conclusion, hope or hype, or I assume hope?
At this moment, I'm still hopeful that these techniques can get us to a level where the results would be acceptable for analog designers.
Who want to keep their jobs and have vested...
Not just kidding. Of course they want to keep their jobs, but there are not enough of them.
Okay, questions from the audience?
Other questions?
It's a great keynote, as always. So, you have this 3-wave, right? So
the third one was halfway. So I left it open.
Yeah, even for the second one, it's not quite go back. From here all the way back here. Still is maybe half there, or is really used, right? So
of course, these optimization techniques are used. They're very powerful. Yeah.
Right. So, but I think one of the keys at that time, sizing has been done a lot. Right? I think one biggest challenge, I guess, schematic. You guys are trying to do something.
The schematic was not the topology synthesis was not. I refer to that as an analogy. Is there is a professor at Stanford who is designing antennas, and typically when people design an antenna, it's a dipole thing, very symmetrical left and right, and she is designing antennas that are asymmetrical, and they are created with machine learning techniques. And then when antenna designers saw the results for the very first time, they said, no, this cannot work because it's asymmetrical and so on. And she proved that it does work. So it's just releasing the constraint that the thing has to be symmetrical resulted in antenna structures that had very specific performance.
Basically, we will go out of designers' comfortable zone. Right?
Yeah, and that's why the explainability is important, because we have to show them that, this is not what you would do traditionally, but it works as well.